Hello, ninth grade. This video is to help you with orthogonal vectors. Orthogonal vectors is just the same idea as perpendicular vectors, where two vectors will meet somewhere at a right angle. Now, look at this slide as long as you need to remind yourselves of parallel and perpendicular relationships when we're looking at slopes. For example, when they are parallel, the slopes are the same. Right here, they are equal. But when we have perpendicular lines, their slopes are negative reciprocals. So one is positive, one has to be negative, and we flip them, reciprocals. Also, their product of the slopes is -1. Keep in mind the product. So let's look at orthogonal vectors today. Vectors that we saw in the parallel lesson, you'll see these four vectors, and notice that A and B are parallel. They could form the same vector relationship. They are both perpendicular to C and D. Now, how do these vectors relate to each other? So let's take a moment and then draw them in our notebook. So vector B is for -6, and vector C is -3, -2. Well, one thing to consider is the slopes. This would have a slope of -6/4 using those dimensions. And vector C would have a slope of -2/3, which we know is the same as a +2/3. Well, look at what happens when we reduce this fraction. This is the same as -3/2. So one slope is -3/2. The other slope is 2/3. And when we multiply them together, -3/2 times 2/3, we get -6/6, which is the same as -1. So that is one way to prove that we have two vectors that are orthogonal. And so what our conclusion would be is that B is perpendicular or orthogonal, also known as normal, to vector C. And we just use the upside down T to note that they have that relationship. Now let's take a look at A and D. So vectors A, which is 2, -3, and vector D is 3, 2. And again, if we look at their slopes, looking at the slope of A would be -3/2, and the slope of D would be 2/3. And remember, if their product is the slope of the products is -1, we have proven that they are perpendicular. So then we take -3/2 times 2/3, and we get -6/6 again, which is -1. So this shows that vectors A and D are perpendicular. So now, can we verify if two vectors are orthogonal quickly? And yes, we can using a dot product. Now this is a special product of vectors. And it is also applied within matrices. And you will likely learn that in future math classes. So now let's learn about the dot product. This is the relationship of the dot product. The dot product takes the components. So again, here is the date and orthogonal vectors. Excuse me. Orthogonal vectors. And so the dot product, good thing to put in your notebook. Dot product. We take two vectors, and when we find the dot product, we are multiplying component by component. So multiply components. And it's really corresponding components. So the x component and the y component. And that is the same as a times c. And then we add them together, b times d. And if that a times c plus b times d is 0, then the vectors are perpendicular. Also known as orthogonal or a normal. Another word for this or term for this dot product is scalar product, just something you might hear in another math class. So let's take a look at an example and find the dot product. So starting with a times b, let's remind ourselves of these two vectors. So here is an example. So vector A is 2, -3. Vector B is 1, 4. When we find their dot product, components, 2 times 1 plus -3 times 4. Well, that's the same as 2 minus 12. And so the dot product is a value of -10, but it's not 0. So not orthogonal. So in this case, these two vectors are not orthogonal. Let's take a look at one more example. U is 2, -3, and now V is 6, 4. Try to do this one on your own and pause the video right now. The product of U and V is 2 times 6 plus -3 times 4. Well, that is 12 plus -12, which is 0. So U is orthogonal to vector B, or vector V, excuse me. Now, let's look at a couple other vectors. Before that, I just wanted to introduce something that we'll talk about later when we look at trigonometry. Why does the dot product tell us that two vectors are orthogonal? It has to do with the angle between the two vectors. We know that if vectors are orthogonal, we have a 90-degree angle in between them. And it applies to the cosine of an angle. And we'll talk more about that when we get into trigonometry. but feel free to read about it. There's a nice proof, just a one-page proof about it right here you can look at, and I'll post these presentation notes as well. Okay, I am going to go through a couple examples from this slide. The first one I want to show you is A. So remember these vectors. Actually, I'm going to write this here. Vector A is 2, -3. Vector B, 4, -6. Vector C, -3, -2. And vector D, 3, 2. If I'm looking at A, I need vector A dot vector B plus C. And so this is the same as 2, -3 times the addition of these two vectors. So add the components, the corresponding components of these vectors, and we get 1 and -8. Just adding 4 plus -3 and -6 plus -2. Now, the dot product is 2 times 1 plus -3 times -8. And that will arrive at 26. So that is the dot product of one vector and the sum of two other vectors. In B, slightly different, we want to find the dot product from A to B and then to C. And what I want you to recognize is that when we find the dot product of two vectors, we get a scalar. We get a number. We don't get a vector. And only a vector can have a dot product with another vector. If we are multiplying by a scalar, that is a different operation. So the dot product can only be done between two vectors at a time. Not possible. The last example that I wanted to show you here was letter D, using some distribution. So 6 times the dot product of D times C. First, we need to find the dot product of C times D. That's -3 times 3 plus -2 times 2. So that is the same as 6 times -9 plus -4. And what is 6 times -13? We get -78. If you would like more examples of dot product, please look at the practice video. Thank you for watching.